Yeah, first of all, I would like to thank the organizers for putting together this wonderful program and also this conference, and also for inviting me to speak. So as Ribu said, today my talk will be about applying our recently proposed fuzzy sphere regularization scheme to study the deconfined phase transitions that many of us are very interested in. And the details of that, so if you're interested in some details, you can check this paper that we posted last year. And the main hero of this talk, of this work is really my PhD student, Zhen Zhou, who is also in the audience. He did most analytical and numerical work, and also want to thank my longtime collaborators, Wei Zhu, who is the major player in this fuzzy sphere regularization scheme, as well as his postdoc, Liang Donghu, at Westlake University. Okay, so let's get started. So this is the outline of this talk. I will start with some brief introduction, like what is deconfined phase transition, in case it's not familiar to everyone here, and then what is this fuzzy sphere regularization, and then I will apply this to study deconfined phase transitions. I will end up with some discussions like whether it's pseudo-critical or tricritical, although I don't think we have a definite answer at the moment. Okay, so just let me start with the deconfined phase transitions. As you may know, that it's a phase transitions that describe some, it's a theory that describes some phase transitions that is beyond the usual symmetry breaking paradigm. In particular, it's a transition between a null state that spontaneously break the spin rotations and valence bound solid that spontaneously break lattice symmetry. And there are a lot of very interesting physics behind it. First of all, you can use some gauge theories to describe such phase transitions. And then a very interesting discovery is that there is indeed an emergent SO5 symmetry for these phase transitions. And the SO5 symmetry is nothing but that you can think those three order parameters of null state and two order parameters of VBS state as SO5 vector. And at the transition, there's indeed this enlarged SO5 symmetries between this 5-component vector. And there are like many different lattice realizations, like JQ models, or there are loop models, and also you can also find some Fermionic models that realize those phase transitions. And all those model realization simulations gives roughly the same similar physics that they has this SO5 symmetries. And they're also like very interesting quantum field theory duality conjectures pioneered by many of the people in the audience. So it's really very exciting and subject that for us to study. But after decades, a few decades of efforts, the nature of this DQCP is still highly debated. So first of all, I think most of people agree that there is no conventional sign of first order phase transitions. It looks like continuous transitions. However, if you look at those results, numerical results very carefully, for example, perform the conventional scaling analysis based on the usual RG, and then you will find there are some violations of those scaling analyses. It may not be the violation may not be dramatic, but it's still not comfortable enough for us to say it's a very nice continuous phase transitions. There are also some other things like if you look at entanglement entropies, that there are some mysterious behaviors that we cannot associate with the usual continuous phase transitions. And if you another tension is that is with this conformal bootstrap that if you just use the critical exponents measured from those lattice simulations, you will find that it's violating the rigorous conformal bootstrap bounds. So there are a number of possibilities that may help to resolve those contradictions. One possibility, one thing maybe for the conformal bootstrap, one thing you may ask is that whether it could be a continuous phase transitions without conformal symmetry, right? So although we don't know, usually we would expect that the phase transitions will have conformal symmetry, but there's no rigorous proof, right? So, and another thing could be that it's a conformal phase transitions, but you have some very abnormal scaling behaviors. And those scaling behaviors make it very hard to get a very accurate critical exponents when you do those lattice simulations. And to me, the most compelling scenarios or proposals is this so-called pseudo-criticality or complex fixed points, and which I will actually explain later. And there are also like possibility that it's actually a tricritical point. I believe you will hear about this in next talk and also in from Shai and also in Anders' talk. And you probably saw Anders' paper last night on arXiv about this possibility of tricritical point. Okay, so now what I'm going to do is that we want to apply our recently proposed this fuzzy sphere regularization to study this deconfined phase transitions. Let me say a little bit about this fuzzy sphere regularization. The original motivation of this is really we want to make use of conformal symmetry to understand, to study phase transitions, 2+1D phase transitions, or even critical phases. And then we really become very excited about this method because it gives us a lot of things that we didn't expect at the beginning. For example, we find that this scheme has extremely small fine size effect. So roughly like 4 to 20 size of model can give you very great results. And more importantly, with this method, we can actually access almost all the information that we care about phase transitions or CFTs. For example, we can get operator spectrums. That's some of those corresponding to the Fermilian critical exponents. And we can also compute OP coefficients. We can compute conformal correlators, like 4-point correlators. We can even compute the famous F functions, which is a 3-dimensional generalization of central charge that monotonically decrease under RG. And we can also study conformal defects and so on. I believe that this list will continue to grow. There are already a lot of new things that we can study using this method. All right, so, and one of the key aspect of this fuzzy sphere regularization is what people call the radial quantization, or you can call it state operator correspondence. It's a very fundamental property of CFTs that you can easily find in any textbook or lecture notes of CFT. So, and the version of state operator correspondence that we will use is on this, this cylinder version, where what you consider is a quantum version or quantum Hamiltonian realization of that CFT, and you put its base dimensions on the sphere as drawn here, and then there will be a time directions, right? So, and under this geometry, you will get a correspondence of the eigenstate of your quantum Hamiltonian with the scaling operators of CFT. Those scaling operators are just the operators that have definite scaling dimensions, and then you can get its 2-point correlators as its power law, and this delta will just be the scaling dimensions. And in particular, for this correspondence, the energy gap will be proportional to the scaling dimensions with some numerical prefactor that is what we call velocity. Okay, so then once we have this realized, to get scaling dimensions or critical exponents, you just need to get energy gaps. You don't really need to do fine size scaling and so on. And you can get a wealth informations of that phase transitions. And in particular, for CFTs, there is a very rigid structure in its scaling operators. In other words, the energy spectrum will have a rigid structure. That is, you can classify your operators as primaries and descendants, where their relations are very simple, that for each primary, you can generate infinite number of descendants, and the difference of their scaling dimensions will always integer spaced, right? That is a direct consequence of conformal symmetry, and then in practice, we can directly check whether we do the spectrum of my Hamiltonian on sphere really have this structure. And once we have confirmed this, we can know that there will be a conformal symmetry for these phase transitions, and further we can read out the scaling dimensions of the operators. For example, if you consider the most familiar transitions, the 3D Ising transitions, then you can find the low-lying primary operators with those scaling dimensions, and they correspond to the critical exponents like eta, like nu, like omega, and so on. And for CFT, there are indeed infinite number of primary operators, making it very hard to study analytically. Okay, so that is the radial quantization, and of course the community knows that, as originally pointed out by Kavli, that we should make use of this to study phase transitions. It's very straightforward to do so in 2D, where you just need to study a quantum periodic chain, and then you can directly get those conformal towers from radial quantizations, and you can also compute a lot of other things. But for 3D, the situation just becomes much harder because a regular lattice won't fit a sphere. Okay, and then our recipe is that to consider what people call the fuzzy sphere, that but to condense matter physics, that's nothing but that we consider quantum Hall physics on sphere and project it to the lowest standard level, and that was originally studied by Duncan Haldane several decades ago. And in this talk, I will just take this perspective, but let me mention that there is very interesting story behind it, like the relation between this fuzzy sphere, or more generally non-commutative geometry, and quantum field theories. Our story may also have some indications along that very interesting direction, but in this talk, I will not really go through any details for that. Okay, so before really discussing the results of the deconfined phase transition, let me just quickly show some results of 3D Ising that when we apply this fuzzy sphere technique to make you convinced that it's a very powerful method. So as I said, what we need to do is that just compute the eigenenergies of a Hamiltonian sphere, and then we can, from energy spectrums, we can get scaling dimensions. Here is the results that we get with, let's say, 16 sites. It's like 4x4 lattice. And then we can, so in those spectrums, we actually get 15 primaries, conformal primaries, and then you can we compare it with the conformal bootstrap results. You can see that the relative error is very small. And I should mention that all those numbers that I listed here is really just raw data. There's no fine size scaling, no fitting, nothing. We didn't do anything for that. So then this agreement is really remarkable. And let me mention that if you use your lattice model simulations, you can really probably just get 3 primaries, like corresponding to eta, nu, and omega. Here we already get a lot of conformal primaries. We can even go beyond conformal bootstrap by computing some parity odd primaries. And even more remarkable thing is that it even works if you just consider 4 sites model. And here's the results that have of all energy excited states of 4 site models. And you can find that, again, we compare it with bootstrap as well as conformal symmetry. You can find that it seems that almost every single state of my Hamiltonian corresponds to a CFT state, and with a very small relative errors, and among those, there are even like 6 conformal primaries. And somehow the primaries usually have smaller numerical adders compared with the descendants. That's something we don't understand why. Okay, so I hope that convince you that this method is pretty powerful and produce reliable results for those to study CFTs. Now let's move to the deconfined visualizations. So let me start by introducing what the model look like, and basically for different type of phase transitions, the procedure to set up the problem is actually very similar. So here for deconfined phase transitions, what we consider is like we have 4 flavor fermions that we call it flavor. You can label it flavor index as from 1 to 4. And then we consider we have those fermions move on the sphere, and in the center of the sphere, we place a magnetic monopole layer. So then the Hamiltonian of this system will be, first we have a kinetic term, just describes the kinetic energy of my fermions. That is a minimal coupling between fermions and the gauge field coming from the magnetic monopoles. And then we have interactions. The interactions are in a form, for example, the first term that we call it like density interactions. So we can define this density operators, which is just psi dagger psi, and it will be a SU4 invariant Hamiltonian density term. So remember that we have 4 components. So in principle, you can have SU4 symmetries that rotate between different flavors of fermions. And then the second term is a bit more complicated. We call it like pairing term, with this pairing, this delta to be like taking this form. And if you are familiar with the symplectic group, you will recognize that actually this term is invariant under the sp2 symmetry. And the sp2 is isomorphic to SO5, or precisely is sp2 quotient A2 is isomorphic to SO5, and then this pairing term is SO5 invariant, but it's not SU4 invariant. So then this Hamiltonian describes SO5 invariant system. So basically that's our Hamiltonian. And then one thing I should mention is that here we have a monopole flux to be 4 pi times S. So the same model actually has been studied before on the torus in those 2 nice papers. And here the actual step is that we put it on sphere for the motivations that I have already talked about at the beginning. Okay, so then we consider the situation that the kinetic energy is much larger than my interaction. And I consider case that I have filled the lowest standard levels. So then what we do is that we can project this Hamiltonian down to the lowest standard level. And in the end, it gives us this so-called, what people call nonlinear sigma model with Western term on the target space S4. And that is what we believed to be one of the descriptions of the SO5 deconfined phase transitions. Okay, so that is the model. And let me also say a bit more about what does the model look like. So after this lowest standard level projection, what we end up with we can think it as 2s plus 1 site fermionic models. Those sites are actually what we know as lambda orbitals on sphere. And then on each orbitals or site, we have 4 component fermions that we can label it as, say, M1 and so on. Okay, and then those fermions are just a hop on this move on this 2 plus 1 site. And one thing is that the projected Hamiltonian actually contains all-to-all interactions, which are organized as using 3G symbols, because we are dealing with a sphere, which will be SO3 invariant. And those interactions are actually called Haldane pseudopotentials, invented by Haldane many decades ago. Okay, and we consider a situation that the fermions are at half filling. It's like, on average, each orbital will have 2 fermions. And this total number of sites is a space volume, this 2s plus 1, and it will be like, if you want to have some intuition with usual lattice model, that will be like L square. L is your length scale of your 2D lattice. And the infinite S will be the continuum limit. Okay. And the last thing that I want to say is the symmetries of the microscopic model. First of all, we have this sphere rotation symmetries. And then each orbitals, each side of those fermions will be a spin S representation of this SO3 sphere rotation. And then there will be SO5 global symmetries, and each fermion will be a spinor will be in the spinor representations of SO5, or in other words, you can easily write down the SO5 vector using those fermion bilinears by properly choosing the matrices inserted here. Okay, and the last thing is that there's a party-hole symmetry, and that party-hole symmetry comes from the fact that I consider half-field case. Okay, so that is how does this fuzzy sphere model look like. Now now let me show some results. Okay, as I said, the first thing that we want to look at are just the energy spectrum, because from the state operator correspondence, the energy spectrums will be scaling dimensions, will be proportional to scaling dimensions with some velocities, and this velocity is not universal, but we can get rid of it by requiring some conformal symmetries of my spectrums. Okay, so here is actually a rescaled energy spectrums by getting rid of this numerical perfector. And the way that we rescale it is recognize that actually for any CFTs, there will be some conserved quantities whose scaling dimension will be protected, will have some, whose scaling dimension is known exactly. So, and here for this model, there will be 2 such operators. One is what we call the suggest tensor, right? That corresponds to the conservation of the translation and the momentum and energy conservation. And then we know that its scaling dimension will be 3, and it will have the SO3 angular momentum 2, and it will be the singlet of SO5. Here, I want to mention that, I forgot to mention that here you can say different symbols actually correspond to different representations of SO5, that here we list the SO5 Casimir of those representations. So we can find the stress tensor. We can also find the SO5 conserved current, which will have angular momentum 1 and scaling dimension 2, as well as it will be a SO5 adjoint. So, and from these 2 operators, we can rescale my energy spectrons to be the scaling dimensions. And after this rescaling, then we can say that the rest of my energy gaps will be just scaling dimensions, of course, plus fine size corrections. Okay, and now then we can start to try to understand this spectrum. For example, if we can look at the lowest operators, which is actually SO5 vector, and then we can say it's a primary operators, and then from conformal algebras like this, we can generate descendants, and we can find all those states. That's how we that's how we understand these energy spectrums, translate that to the, for example, the operator spectrums of CFT for this deconfined efficient divisions. All right, so now let's look at results. The most important results I want to highlight is these conformal symmetries. And so as I said, we'll have a stress tensor, we'll have the conserved current, and then we have the integer spacing between the primaries and their descendants. Here is the results for 2 different primaries and their descendants. The first one is the SO5 vector, that is an order parameter of the deconfined visualizations. And you can see that here is a result with that plot a different system size. Now you can see that from the primary and those lines, actually what you should expect theoretically for the integer space descendants. And you can see that those numerical data agree with what we expect for the conformal symmetries. It's actually very non-trivial requirement because there are so many states. And here is the results for the conformal multiplet of the conserved current, SO5 conserved current. Again, you can say the primaries and their descendants and the numerical data agrees also very well. Okay. Yeah, so that's a good question. So here, basically, what we did is that we try to find a point that we have both stress tensor or conserved current, or in other words, the gap will have a ratio like 2/3. Yeah. So okay, and indeed, we can go much further beyond what I just showed in the previous slides. So here is a energy spectrums of like 8 sites, whereas the lowest 100 state, and among these we can actually find 19 primaries and 82 descendants. That's really a very strong evidence for the emergent conformal symmetry. And among those, we can also get a lot of primaries, just as what I showed for the Ising case. And those results have several interesting physical consequences. One is that if you look at the results of the last row, and it's parity odd or time reversal odd operators, and you find that it is highly irrelevant. So that means that for deconfined phase transition, if you break time reversal symmetries, for example, add a scalar parity, nothing will happen until you make that term very, very strong. That's very different from what we know, what we called U1 Dirac spin liquid, where this operator is believed to be relevant, and also numerical simulations also support that. And another thing is that this fourfold monopole is what in the convention of the CP1 model is actually irrelevant. That means the DQCP is stable on square lattice. That was the original proposal for the DQCP story. And the other thing is that the threefold monopole is relevant. So that is suggesting DQCP is unstable on the honeycomb lattice. Okay, so that is a physical consequence. But now we want to try to address the question that what's the nature of DQCP, right? So here I think at least to me, a very, very convincing claim coming from our results is that, first of all, the conformal symmetry is indeed emergent, right? And secondly, is that the DQCP will stable against this time reversal breaking. So I think for those two statements, nothing would be wrong there. But we still haven't answered that whether DQCP is critical, tricritical, or pseudo-critical. So let me maybe spend 5 minutes-ish, try to have some discussion on this. So the first of all, one thing I should mention is that here our model have explicitly SO5 symmetries. So then really to use the language critical, tricritical, we're actually talking about attractive fixed point or repulsive fixed point in the SO5 invariant line. So for example, if DQCP is critical, it will correspond to a RG fixed point like this here. And if you break the SO5 symmetry, then it will follow to either nil or VPS. But if you stay in the SO5 invariant line, like what we are doing, 1 minute, and then it will become the critical phase. Yeah.
Just to clarify, when you're using this terminology critical, tricritical, you're referring to it from the perspective of the SU2 cross 1.
Yeah. Right. That's why I'm making this clarification here. Okay. So now that's ask a question that for the DQCP, whether it's critical or tricritical or pseudo-critical. So that's first think about on the field theory, what's the question? So as we know, we can use gauge theories to describe DQCP. That was also the original proposal. And those gauge theories typically will have one parameter that is called flavor numbers of either fermions or bosons. And for that, we know if the flavor is very large, the RG flow diagram will like this. I will have some symmetry breaking, fixed point, and then I will have two conformal fixed point. One is repulsive, the other is attractive. And for the critical DQCP proposal, that means it corresponds to this attractive fixed point as what I have explained. And then we know that if you decrease your fermion flavor, those two fixed points will start to approach each other, and eventually they will merge to a single point, and after which one likely scenario is that they will collide and disappears in the real axis, but they will go to the complex plane as shown here. And then the pseudo-critical proposal is that if those complex fixed points are close enough to the real axis, and then even if you don't even if you just study a Hermitian system, you will still see the consequence of this complex fixed point. It will give you a very give you some signatures of continuous phase transitions with some subtle, very unconventional RG flow. So that is a pseudo-critical proposal. And one key thing that I want to point out that although we don't know when this collision will happen and also and many other details, but we believe that the fixed point will disappear in pairs. And there's no mechanism that for critical point disappears, but a tricritical point survives. There's just, we don't know any mechanism for that happen. Okay. Yeah. Okay. And maybe 5 minutes. Okay. Yeah. And microscopically, you want to, maybe after this, let me show one or two slides. Yeah. So, and the microscopic model, on the level of microscopic model, the question that you do want to ask is what's the phase diagram of those JQ model or fuzzy model? And that question is actually slightly different from the quantum field theory questions. So, and it could be that in the end, it still is a true critical point, DQCP a true critical point, but for some mysterious reasons that we are always forced to explore regions, like here, close to a tricritical point. That could happen, but there's no compelling reason to explain why it always keeps on happening. And to me, the most natural scenario is that the pseudo-critical scenario that, as I have explained, and also it could be a tricriticality there where the pseudo-critical region still exists, but for some models, you can actually tune it to some new critical point like this, and you are kind of similar here. That's possible, and I think that is the possibilities for this tricritical proposal. Okay, and one thing that I should say is that from our results, the SO5 singlet is very close to marginality, as you can show here, and this observation is consistent with either pseudo-critical or tricritical proposals. But if we can look at more. But again, if you look at this singlet more carefully, you will find that it actually flows from slightly irrelevant to relevant. That is probably more consistent with pseudo-critical. Yeah. So we can also understand it from conformal perturbations. We can do some data collapse to say this pseudo-critical behaviors, and let me just summarize. So we apply this method to DQCP and find a very strong evidence for conformal symmetries. And we did further analysis that is in favor of pseudo-critical scenario, but the tricritical scenario, so at the moment we cannot really completely rule it out. And I think for the pseudo-critical proposal, the missing piece is that we do want to find the complex fixed point exactly. And that has been done indeed for the 2D 5-state pulse model, as you will hear from Han in the afternoon. And for the tricritical proposal, there are two missing pieces. One is that we do need a new field series. You cannot use in CP1 and say it's tricritical. I don't think it's theoretical. It doesn't quite make sense. And the other thing is that you do want to directly, in the lattice model simulation, you want to directly access those two fixed points. In particular, for this fixed point, it will be some spin liquid phase that we need to identify as well. Okay.
Thank you. Okay, so we have a lot of questions, but can I request you, Leo, to use that mic, the mic behind there? In fact, if you stand there, the camera person will be most happy because. So if you have another question, if you want to get ready and get close to this mic, because the camera will record you.
Yeah, just a quick question. So the Hamiltonian you wrote down, the fermionic one, that's automatically at the critical point, or is there another another operator that tunes you away from it?
Yeah, we need to tune it. For example, you always say there is a parameter like V over U. V is a SO5 breaks the SU4 to SO5. And then we tune this, and we find that there's a region that has very good conformal symmetry, and we explore that region. Yeah.
Okay, thank you. So if I may just follow up on that question, so is this point where there's good conformal symmetry, is it a single point, or is it a large region over V over
Yeah,
U?
I didn't have time to measure it. So here is actually we find this in a very large region. It has very good conformal symmetry, and we don't find any other signatures of any signature of another fixed point. That's why we think it's more likely to be pseudo-critical. Because, yeah, for pseudo-critical, you naturally expect this.
Okay. First Max, and then.
Can you show the slides where you do the data collapse favoring the pseudo-critical scenario?
This one?
So can you talk a little bit about this, please?
So first of all, from the conformal perturbations, like here we model the system as a fixed point Hamiltonian plus some perturbations, right? And then we can get the free energy or energies for different perturbations, lambda, right? We can get these results, and then we solve beta functions and so on. We get for a complex fixed point, what should this scaling dimension look like, right? And then we use this to do the data collapse here. And here it's like V over U is just a tuning parameter for us to access different point of in our phase diagram. And then this lambda is just the coupling here, right? And then we try to fit this lambda by using this formula coming from the conformal perturbations for complex fixed point. And those C1, C2, C3, this alpha times y squared are the free parameters for us to fit. And then you see there are a lot of data here, right? And then, all those data are fitting just with those few parameters. Yeah, and then we collapse all the data here. Yeah.
So the scaling dimensions still correspond to energy levels,
even
in this, at least to this order.
Yeah.
Thank you.
Yeah. I wonder if it's a pseudo-critical point, whether the conformal symmetry won't be emergent. You emphasize you'll see the emergence of conformal symmetry.
Yeah.
That seems to me contradict with the pseudo-critical results.
Yeah, good question. So if it is pseudo-critical, you will get exact conformal symmetry at those complex fixed point. Yeah. So here we are only exploring the real Hamiltonian, Hermitian Hamiltonian. So then you will not get exact conformal symmetry even in the thermodynamic limit. So in our paper, we call it approximate conformal symmetry.
Okay.
But it's really a question that whether the complex, the fixed point in the complex plane or in a real axis, that's a question we cannot answer at the moment.
Okay. Yeah.
Right. But I think it's clear to say that conformal symmetry will be somewhere very close to the parameter point we are exploring. Yeah.
I see. Thank you.
I wonder if you could comment on the extent to which pseudo-critical and what you call tricritical are mutually exclusive. I mean, they could both be right, under certain, in the context of some more broader set of field theories.
That's what I'm drawing here, right? Yeah. So then it could be that in some lattice model, like what Anders is exploring, that there will be a new fixed point, right? There will be two new fixed points. This fixed point will be some spin liquid phase, which could be either chiral spin liquid or even some Gapless spin liquid, like Z2 spin liquid, Z2 Dirac. And then there will be a critical point between this pseudo-critical region or symmetry breaking and this spin liquid phase. I think that's totally possible. Yeah. But as I said, it requires more evidence to support that. Yeah.
Masaki.
Yeah, sorry, could you remind me again, definition of this G equals to V over U? U and V were original.
Here the V and U are really just those two terms. Sorry, I should go. Yeah, V are this term that breaks the SO6.
Yeah, I asked because in the original proposal of DQCP, that was a critical point appearing between, let's say, NER and VBS.
Yeah.
Then those are, SO3 or SO2 SSP phases.
Yeah.
So that NER to VBS transition in original quantum magnet is not the same as this G-axis.
Right. Our axis is SO5 invariant. In the usual lattice model, is in this vertical direction.
So you are looking at this horizontal direction.
Yeah.
Thank you.
Can you say what you would expect to see in your data if there was a weak first-order transition?
Sorry, I missed the
Can you say what we would expect to see if there was a weak first-order transition?
Yeah. Okay. Here, by pseudo-critical, I mean it's weakly first order, and then a number of evidences like this, such like a vast region of conformal symmetries, as well as this RG flow of my singlet, as well as this data collapse. They are all in favor of this weakly first order phase transitions. But I think more conclusive evidence will be find that complex fixed point directly.
Thank you.
Okay, we have time for one more question, and I'm offering room service. I'll come to you with the microphone. If you have one last question for Yinchen before we move to our next talk.
So logically, is there another scenario like there's a multi-critical point between the weak first order and the strong first order?
I don't say such possibility.
Why is that?
Yeah, I cannot find a field theory for that. Let me put it that way.
Okay.
Yeah.
But so do we have a field theory for the scenario C that you have?
Yeah. I think one possibility is really that
QCD or
let's say this fixed point is chiral spin liquid.
Yeah.
Then we know this will be this QCD3 cross the U.
Okay.
If it is some Z2 Dirac spin liquid, maybe Subir has some theory. I'm not entirely sure, but yeah.
Okay, let's thank Yinchen again for that great talk.